what are the objectives of today? Well, it would be great if today you would actually end this webinar by knowing, okay, this is CFD. I know a bit more about computational fluid dynamics. I know what it means. But more important is that you actually have an idea about the practical value. Which practical problems can it solve at full scale, at pilot scale, sometimes at lab scale? And also next to the application side, what is the current state of the art? And I think this is a very relevant question. Why? Because if you look at digital tools in general, computational fluid dynamics is just one of them. Well, they evolve quickly, and in a matter of 5 to 3 years, a lot can change. So this is why it's very important for you also to have an idea about the state of the art. So we will really share the latest developments and really very recent case examples here that probably most of you are not really familiar with yet. Okay, so I am Wim Oudenaert. I'm a Belgian. I'm also right now talking from inside Belgium to you. And I'm co-founder and CEO at Aeration. So this company, I will give a very short introduction on that, but that's not the most interesting thing. I think the application side of CFD is more interesting. But anyway, I co-founded this company together with 2 other colleagues. And then we also have 2 moderators here. You will hear them from time to time. So it's Daria Sudrowska. So she's actually now joining from Poland. And then we have Giacomo Bellandi. He's actually joining from Italy. So we have quite an international, let's say, team here, but also you as an audience are very international. That's what we know. We have a lot of continents here being represented. So that's really great. Huh? It's really great to see so many people from different countries. What is very important here is, well, I will be talking a lot. I will be presenting a lot of cases, a lot of slides. But on the other hand, it would be great if we have some interactive discussion. So if you go over your screen, you will see actually the possibility to ask questions in the Q&A. So you can ask questions in the questions and answer, the Q&A field. And the moderators, Daria and Giacomo, will be continuously monitoring them. And if there is really a good question that is relevant and at a specific slide, Daria or Giacomo may even interrupt me, and we will answer these questions live. So we will do this as much as we can. Okay, so I really encourage you to really ask a lot of questions. Don't wait. You can also, I think, even choose the options to ask a question anonymously if you want. Okay, after the webinar, a short questionnaire will appear because we are continuously want to improve, and we are, of course, very interested in what you think about this. Okay, let's go to the, let's start with a small poll. I'm actually a bit curious what your backgrounds are. And normally on your screen right now, you should see the option to vote. So there are actually 2 questions. It would be great if you could answer these questions in the coming, let's say, 20, 30 seconds. So Giacomo, can you actually see the poll correctly?
Yes.
Okay.
That I can see the
okay.
poll. Yeah.
Great. So people are now voting. We are getting some statistics in. Okay, so that's quite interesting. Huh? The stats that are developing here. So I will give a word of explanation here. So most of the people that are joining, and I'm talking about, let's say, somewhat more than 50%, or it's changing. So 50%, let's say, actually doesn't know too much about CFD, or at least has never applied it. And then we have 50%, or like 43%, they have used CFD in the past. And the main reason for attending the webinar here is like the biggest chunk of the people, 43%, is they want to get a general overview of the applications. And on the other hand, we have another 35% interested in CFD for process optimization. I think that's very good to see, because that's really the target audience here. Huh? So we will really do our best to answer these questions. Great. Good. What is the content? Short introduction on AM team, on our company. But I mean, it's very small font, so it's only 1 or 2 slides. Then what is CFD? Some basic understanding, because you have to understand some basics before we go to the cases. And then we will see a huge amount of case examples. So we could actually do this webinar in two directions. We had two options. Either we show you a few cases and we really go deep, or we show you a tremendous amount of cases and we stay a bit more on the surface. Well, given the background and the expected audience here and our experience also, it's much more valuable for you, we think, to see a huge amount of cases that you have a very good idea about which questions it can ask and for which technologies and processes it can be applied. Okay, Q&A, very big font, so it's very important. All right, AM team. Well, the name actually comes from the A-Team. If you are not familiar with the A-Team, well, that's like a special force. It's a US television series from the past. But our company really wants to do a very unique offering to the market. We offer, let's say, very realistic process simulations to the water industry. And we help actually people with process optimization, process design, and scale up. And you will for sure be familiar with some of the logos on this slide. Others are maybe more unknown, but you can see it's a whole variety of companies that we work with. But also you can see on the little map in the left-hand corner that our customers are really from all over the world. We are actually serving people from 4 continents right now. So it's quite international because of the core focus on process simulation. So we are very good at computational fluid dynamics, but really dedicated to the water industry or process side. And this really is really quite unique. Okay, so last slide on the company. So I promised to really keep this short. We have around, well, somewhat more than 50 customers right now, more than 80 projects finished in the meantime. And well, generally our customers are really happy. So these are really the average scores of our customers in the last 2 years from all the projects we have finished. And it's consistently close to 90 or above 90%, 9 out of 10, which is great to see. Okay. But again, we have a huge amount on our website of information. So this was all on the introduction of AM team. My personal background is process technology, process modeling, drinking water and wastewater. I have worked on both. And I have a special, let's say, specialism, a PhD in advanced oxidation processes for micropollutant removal. But generally it's physical, chemical, and biological wastewater and drinking water treatment. Good. What are the challenges probably you might face with process operation design and scale up? Well, if you look at the water or wastewater treatment process, or actually a treatment of production process in general, you have a lot of challenges as an engineer. Most of us here attending are engineers. And well, you have to actually design a system. And you design a system for optimal performance. And it means a system that is as small as possible, reliable, your water quality is optimal, and you also preferably have not too much operational costs. So that's the dream of everyone. But you have to make a lot of decisions. Shape of reactors, impellers, and then you have water, you have bubbles, you have actually particles or solids, and then you have reactions. And all of these things are actually combined in most of the water and wastewater treatment processes. Not all of them, but let's say it's a mixture of them. And it leads to highly complex processes. And then we have combined with that dynamics. And I mean, the demand or flow rates also change. So if we look at the operational side, well, a plant also varies in capacity. So there is a huge challenge here. And the question we want to actually solve with our company, and we actually have done a lot of cases on this for customers in the industry, is what if we could reduce, complement, or replace real life experimenting and piloting with a very realistic process simulation? And I specifically mean computational fluid dynamics. Well, why is this question very relevant today? And why is your attendance today a bit more relevant than, let's say, 10 years ago? Well, because CFD or computational fluid dynamics or modeling in general has matured a lot in the last decade. Computers are very fast now and the models have been developed a lot. And there are, of course, also a lot of practical case examples that just show the benefits already. This is a very relevant question. Why? Because if you are involved in practical testing, practical measuring, experimenting on site, piloting, you know that it's very time-taking, it is very laborious, it is sometimes stressful, and it costs a lot of money. I'm not saying that it is useless, and it can be very useful. On the other hand, what I'm saying is, what if you could replace part of that, and in some cases almost all of this, by very realistic simulation? Well, it's worth asking this question. It's really worth asking this question because it's about a lot of time and money. Okay, so while using CFD, you can do actually a plug and play of what we call our gears, the gears. So based on the project objective, you actually have the water phase, but also you can include particles, solids, for example, granules, granular sludge, flocks, crystals, or the gas phase, for example, ozone, oxygen, air. There are a lot of gaseous systems as well. So depending on the project or case, you actually do a plug and play of these. It can be all of them or just one of them. But also you have the possibility nowadays to include kinetics in CFD. So you have the 3D conversions of something. It can be oxidation, biological conversion, bacterial regrowth. So these kinetics can be directly coupled with CFD, which gives a lot of insights. And then you have the process settings. Viscosity, temperature, reactor dynamics, reactors, impellers, etc. So what is CFD? Well, you start actually from a real system or a system you want to build. So it shouldn't be existing yet. And then the first step in CFD is just you build a geometry. We call this the 3D geometry. It's somewhat more simple than a real CAD drawing, let's say, but it contains the real essential elements. And I mean impellers, mixers, aerators if you have them, the size, the real size of the system, the real flow rates, etc., etc. So this is what we start to build, and then this is what we call the meshing. Yeah. So I'm just explaining on this one slide what CFD basically means. We will not go into detail, but then we do the meshing, and you divide a whole domain. So if you, for example, have a reactor of 1 million liters or 1 million cubic meters, we have actually simulate big systems as well. And you divide it in 1 million cells. On average, the cell size is then 1 liter or 1 cubic meter. Yeah. So it's high resolution modeling. In each of these cells, you solve physical equations, and this leads to a very detailed, of course, hydrodynamic calculation, because all the cells will actually calculate mass balances, and you will have the very nice plots coming out, which most of the people are familiar with the colorful drawings. So CFD, that's a bit the power. It visualizes nicely, in this case, for example, where the bubbles are. So this red zone, which you see here, is a concentration of bubbles in an aerated zone or oxygen. And you have in the aerated zone other zones with a bit less bubbles in this case. But it can be velocity, it can be velocity gradients, it can be different things. I will come back to that. Very simple example. This is from the drinking water field. You have a reservoir, we fill it with some drinking water. This is a drinking water storage system. You don't want the drinking water to be aging because there is a potential risk on bacterial regrowth. So it's all about risk minimization. You can, of course, nicely visualize how the newer water that comes in mixes with the older water. And at the end, if you cut the water tower, this water reservoir, into slices, these are horizontal slices at different depths. You can see the green zones, which are actually the older water from the day before that is still in there and not completely mixed with the new water. Yeah, very simple system. But what is the value of CFD is that, well, you can actually do what-if scenario testing. We call this what-if scenario testing. So what if, for example, in this system, we would make this pipe a bit longer? What if we put it a bit deeper? Would it improve the system? But you don't have to do this in practice because it's not feasible in many cases at full scale. And secondly, it costs you a lot of money and you still don't know if it will work. So you can first simulate it, and let's simulate it. And then you can see, for example, that the new design is much better. This is the new design with a central filling. It's just changing a filling pipe. And then you can actually see, if you look at the old versus new water ratio in the reservoir. The blue line, you would have actually if the water tower would be completely mixed. Just imagine it's an ideally mixed system. Everything is perfectly mixed. What you can see is actually the original design had much more newer water at the bottom because the red curve is deviating a lot from the blue one negatively. In the middle of the water reservoir, you had a lot more older water packages, and then at the top zones, more or less 50-50. But if you optimize it, you come much closer to the optimal system. Okay, what can you actually change? You can change actually any operational variable or any design variable of your system. And this is what, of course, makes it a lot of very attractive. And I'm coming back to the question, what if you could replace physical testing? Well, here you have the testing freedom that the simulation actually offers you. You can test mixers, mixer types, impeller speed, how many mixers, how many propellers, how many aeration devices, where do you put the inlets, what is the perfect reactor shape, where do you put aerators, what is the impact of viscosity, what is the impact of many other things. So these things, baffles, dosing locations of chemicals, you can actually vary all these things to answer a lot of questions. Okay, this is what you actually put in. What comes out is most of the people are only familiar with mixing patterns, some velocities. So let's call them dead zones or short circuiting. How is the mixing? But CFD is much more than that. And I'm just giving this slide to give you an idea on what actually can come out of CFD. We have used all of these variables in all of our projects, well, across projects, not all together in one project, but we have used all of them. And it means you can inject a virtual tracer in your inlet and look how it distributes in the system. So you have a very direct quantification of the mixing efficiency. You can visualize concentrations. For example, this is a bioreactor, a big industrial wastewater treatment facility, and the local dissolved oxygen concentration, or ammonia, or nitrates. If you couple kinetics with CFD, you have these 3D plots. And if, for example, your dissolved oxygen sensor is located in this red spot, well, it might not be at the representative spot. You can look at particle depositions. For example, this is the top of a sand filter where the particles actually settle on the bed. Particle transport. So this is a huge basin with solids being transported. People in the drinking water company want to avoid the solids coming out again. They want them to settle. You can look at gas holdup. So if you have an aeration system, where is your gas actually, how is it distributed? And what is the impact with upstream or downstream mixers? And sometimes they really fight instead of collaborating. You can look at velocity gradients. I'm thinking about coagulation, flocculation. You can look at shear distributions. I'm thinking about membrane filtration, so shear on a membrane surface, etc., etc. There are actually 4 reasons. We have really defined 4 core reasons people use CFD. Well, I already mentioned it a bit, to save costs, to save time, of course, to end up with the optimal process performance. And also, if you are a technologist, and the fact that you actually are now attending this webinar means that you want to learn a bit more about it, while probably you are also interested then in really understanding what's going on in your process. Most of the process people, they have a passion for process. They really want to understand. If you have a better understanding, you also increase your confidence a lot. And so this fourth one is also a very important one. Let's now go to the most interesting part of the webinar, the applications. So I want to mention that we only selected some cases. It's a lot of cases, but we have to make a selection, and the variety is enormous. Huh? So the blue ones, which you see on the slide, are more, let's say, wastewater related, and the purple ones are more drinking water related. But there is a lot more examples. I'm just showing this slide because you can see, okay, it's about aeration processes, membranes, solids, for example, anaerobic digestion. It's about small systems, large systems, fluidized beds, sludge blankets, crystallizers, etc., etc. So it's a huge variety of systems. Okay, let's go to the case examples. First example is a scale-up example. So we will be talking about an MBR in this case, a membrane bioreactor. So even if you're not working with MBRs, just look at the scale-up. So what we are here doing is using computational fluid dynamics to accelerate the scale-up of a new technology, and while actually saving a lot of pilot tests. Yeah. So we try to save a lot of pilot tests here by replacing it with very realistic process simulation. So we had a Japanese customer. They actually developed this new MBR. I will not go too much in detail. It's a one compartment MBR, and the volume actually varies throughout time because they fill only once. They fill it with wastewater, so here it's full. And then the permeate starts, of course, being drawn, and the air is going over the baffle like this. So the aerator is at the bottom, air is going over the membrane, and the air also circulates right like this. The whole reactor volume is aerobic, oxygen everywhere. But suddenly, at a certain point in time, the water volume or the water level reaches the baffle, and so the oxygen cannot go over the baffle anymore. So this outer zone, this outer shell of the reactor turns anoxic because the activated sludge will consume all of the oxygen. So they play with gradients in one reactor. Well, they had a very successful system at pilot scale. It's a 3 cubic meters pilot, and they wanted to scale it up to 100 cubic meters, which is actually 2 orders of magnitude larger in scale. Well, then you have the question, what will we do? Will we build extra pilots? But it's not so straightforward because you have so many degrees of freedom in your design. Cycles, filling time, emptying time, the rate of aeration, the shape of the reactor, the numbers of inlets, inlet diameter, baffles, the height of the membranes, etc., etc., etc. If you want to test all of these things during piloting, it's practically infeasible. It will take you too much time, and you will have to build a lot of pilots. And still, at the end of the road, you're still not sure about the best design. So what we did is actually build a very realistic model. It includes the biokinetic conversions. So we will directly calculate permeate quality. It includes the bubbles. It includes the high viscosity of a lot of sludge in an MBR because these sludge levels are higher. This is a conceptual simulation. So the bubbles go up over the baffle. It reaches the baffle here, and the oxygen goes away at the left side. Now you see the depletion happening. So you see that's a transient, which we call a dynamic CFD simulation, very realistic. And in the end, we scale it up via the computer actually. And then we start virtually designing the ideal full scale without having built it in practice. So what we do is here on this right graph, we are comparing the permeate quality. So of course you want the BOD, ammonia, nitrates to be as low as possible. So we are comparing the performance of 5 different full-scale designs. So all of them have the same treatment capacity, but only one of them is the best performing one. And the only thing we changed here is the aforementioned factors like membrane height, baffles, shape of the reactor, etc., etc. At the left, you can actually see that you have local zones this is the ammonia profile at one specific time in the cycle. So it's just a snapshot. Okay, let's zoom in on membranes. This is just to show that you can go a very high resolution. You can look on the membranes. Again, a lot of design variables. We had a Belgian customer here designing new flat sheet modules, the IPC membranes. What you want here is equal bubble distribution over each of the flat sheets, that none of these membranes starts falling. Over one sheet, you want actually an equal shear distribution. So the ideal membrane would be one color, if this is the shear, the shear force. And then across the module, you also want every sheet to be scored equally. And again, you can choose with aerators, the shape, the design. You have a lot of design variables, let's say. So we did a lot of CFD simulations here for this customer. Again, without them having to test it in the lab, in their facilities. So we tested, for example, fine bubble, coarse bubble aeration. You can see that coarse bubble aeration gave much more shear on some of the sheets. So each individual curve here is the shear distribution over the membrane surface of one membrane sheet. If there are 30 sheets in one module, you have around 30 curves here. Ideally, the curve is vertical because you have the same shear across one sheet. And ideally, every curve is the same. Then you have the same membrane shear across the whole module. But you can see in reality, it's not like that. But in the coarse bubble aeration case, it's really a disaster. Well, because some of the membranes have all the shear, which is, for example, this right one. And then you have some membranes without any shear. They hardly see any bubbles. And with fine bubble, well, you have a little bit less shear, but it's much more average. And this was really the way to go in this case. Yeah. We can look at different systems, fluidized bed reactors, for example. You have a lot of them nowadays. This is one example in the drinking water industry. So it's a pellet softener system. They use a pellet reactor to make calcium carbonate precipitate on the surface, and then you get these particles that actually precipitate. Yeah? Well, you can have similar systems, for example, granular sludge, anaerobic upflow reactors, struvite reactors, crystallisers of any kind. There are a lot of upflow systems. And again, with CFD, you can actually do some nice simulations. You can see the high velocity at the bottom, lower velocity at the top, okay? And the questions typically here are, can we lower the size of the reactor? Because it will save us a lot of money. But in this specific case, for example, our client was putting these types of reactors in decentralized areas with a lot of people living around. Well, they hate these very tall reactors in their neighborhood. So if they can reduce the size with 2 or 3 meters, it's very nice. Of course, optimal kinetics. Can you optimally stratify the granules? Can you avoid short circuiting of the water or of the chemicals dosed at the bottom? Because you often dose chemicals here. A lot of questions. And again, it's a scale that you will not easily pilot at, because these reactors, for example, in this case, are 12 meters to 15 meters of height. It costs a lot of money only in stainless steel without even operating them. So you will preferably make not too much mistakes in your design. Again, you can build a CFD model. I'm just showing this case because not many people realize these things can be simulated today. Most of the people are only familiar with mixing or aeration applications. So you can include the solids. We have actually virtually filled this reactor with granules of different sizes, ranging from 0.25 millimeters to 2 millimeters. So it's a whole distribution in density and size. We add them to one system and we look at the classes separately. So it's all in one reactor, but we just visualize the classes in this graph separately. Of course, the biggest ones are at the bottom and the tiny particles are at the top. It makes sense, but you can also see that they are a bit everywhere. So it's not ideal stratification. Of course, we looked at the chemicals, etc. also, but you can derive a lot of quantitative information from this, which you cannot really easily measure, for example. This graph shows you the volume fraction of each of the classes as function of the height of the reactor. So if we look at the bottom between 0 and 1 meters of height, of course, the red and the orange curves, which are the biggest ones, 1 millimeter and 2 millimeter, are most dominant. And then, of course, if you go higher up, you have a lot of smaller particles. And you see a lot of steep falls of particle classes because of this reactor shape, which you see suddenly increases in width. Yeah, so these design aspects have a lot of impact, of course. Yeah, I'm just showing this that you can make a lot of quantitative graphs next to the colorful drawings only, because it's not always easy to only based on the colors to make a lot of decisions. This is what we currently use to optimize these reactors, come to an ideal design and a standardized design that really works optimally at the given customer's site. I will pause for a moment and just go to Giacomo and Daria and ask if there are any questions in the meantime.
Yes, yeah, there are quite some questions popping up. Maybe one thing that we want to answer straight away. It's important to clarify this point. It's what is the approach to select the most important parameters and eventually the number of cases to be simulated. So the question is about how do we select the design parameters and the scenarios to run?
Yeah, of the technology, right?
Exactly.
Yeah. Yeah. Well, typically we have, if we are, it depends a bit on the case. If we have optimization cases, for example, we as a company will do a lot of suggestions based on prior experience with process optimization. For example, we already know this mixer should be put there, or maybe another mixer type would be better. So we can give a lot of suggestions. On the other hand, when we, for example, it depends a bit on the customer as well. If the customer has a lot of design knowledge or also wants to stay in the lead there, well, it's a very close collaboration we have. And what we typically do first is we agree on a standard design first. So this is the first design we will simulate with the customer. We simulate it, and then we will look at the results together. And after looking at the results together, we see, of course, most of the times, a lot of problems with, or let's say, opportunities to improve. And then we generate a couple of priorities together, inlet, outlet, with the customer. And it's based on two criteria. First is, what do we think if we now change this, what will be the potential impact? And it's again based on a lot of experience. For example, if it's a quick win, mostly is changing a mixer location, for example. You don't have to change too much for that in some cases. And another criterion is, what is the cost for this? So typically we will start changing the things that are most easy to implement in practice and cheapest for the customer, of course, in the design. And then we will gradually build up. So it depends a bit on from project to project. It's a mixture of experience. And then we look at the costs, of course, of the measures to be taken. For example, if this design works better, but it costs double, well, it might also not be the best choice. Huh? So it's a mixture of performance and cost. And this is where this close collaboration with the customer, in many cases, is very, very important. Yeah. Okay, so in some cases we go really far in suggesting, and in other cases our customers give most of the suggestions, and then we have some cases in between. But it typically comes down to these two factors. Did that reply the question, Giacomo?
Yes, I think perfectly.
Okay.
So one other interesting question that we can answer before proceeding with the presentation is from Jan Post. You're talking about shear distribution in membrane systems. Are you also able to model flux distribution over a membrane system? And how would you deal with spacers, the turbulent promoters? Mm-hmm. Would the model not become too heavy?
Yeah, very good question. So Jan, also thanks for attending, by the way. Yes, you will, of course, need a different, well, you can look at the flux distribution. We have done that for a couple of membrane applications. I think 3 different projects we have looked at flux distribution, hollow fibers to tubular membranes to flat sheets, inside out, outside in. If you look at then the spacers, well, indeed, you will need a different type of CFD model because the question you want to answer is different. Probably the question you want to answer there is, what is the best spacer here? What is the best spacer design causing best turbulence? You can use a different model for that, and you have a lot of choice in CFD models, of course. It will be probably a heavier model, more resolution, but on the other hand, we have also cloud computing. And I mean, I will give an example here on the next slide of a 3-phase CFD simulation full-scale transient, which is also very heavy. So yes, it will be heavier for tracers, more detailed CFD simulation, more detailed turbulence modeling, but it's feasible, and I would say feasible within reasonable time. Yeah. Okay, so well, let's look at a case that might be surprising for many of you: sand filtration. Because of why? It's the oldest. It's really the oldest reactor treatment technology of all of the water and wastewater treatment technologies. It was invented by, well, it was already in use by the old Greeks, and I'm talking before Christ, many years. So it's a technology of thousands of years old. And the first sand filters were actually ships. They filled the ship with sand, they put some holes in the ship, and the water was filling in the ship and went from down under to the top and was filtered like that. These were the first sand filters. But then if we look at 2020, after Christ, well, we still are struggling with a bit. What is now the best design of a sand filter, of a rapid sand filter? Shape, aspect ratio, inlet gutters, water height, etc., etc. There is a huge amount of cases, huge amount of, I think maybe the technology with the most types of designs. Well, here you can actually look at the filtration cycle. Where do particles preferably settle? Is the particles distribution over the sand bed homogeneous? But this is this was the simulation I was talking about. It's one of the oldest technologies being simulated with a very modern simulation tool. And this is why I like this case. What you can see here is the nozzles at the bottom. So we are looking, it's a 3D simulation of a sand filter, of a square one in this case. We are looking at one slice vertically, and the nozzles, which will backflush, are at the bottom. Okay, we start backflushing. You see the expansion of the sand bed. Only water, so we will start with backwashing with only water, and then we add air, and then you see, of course, the whole turbulence changing. So this is really, strictly speaking, a three-phase simulation, which is, I would say, globally unique. We have seen no other case where this has been done, but you can see that the level of reality is really cool. Well, we are now looking at, with our customer Vitens, it's a Dutch utility, can we standardize the designs? For example, can we just select one type of design that really performs well, and nozzle placement, gutter placement, aspect ratios, how do we introduce the water, what is the outlet gutter design, such things. So these are things we are looking at. Yeah. So you can even go to dual or multi-layer filtration here. No? I'm just showing this example because you can today go very advanced in CFD. And coming back to the membrane spacer, I would say that this is an equally heavy CFD simulation. Yeah, and we are still doing it, but of course we use cloud computing here. Huh? We put it on the clouds with a lot of computers, but again, this is all available now. Good. I will come back to Giacomo before we go to the next cases. Are there additional questions?
So maybe, yeah, one that we can answer before going further. So it's a specific question on slide 31, actually, from an anonymous attendee. I was enjoying the interesting case, and he's asking if a four-way coupling approach is needed to simulate this case. I'm not sure what a four-way coupling approach is, but
yeah, what might be the question here is, for example, the granules here are growing throughout the cycle. Yeah, more calcium will start attaching. Your pellets grow. It's in reality, it's a dynamic system. I think the question relates to: do you actually include the kinetics, precipitation kinetics? Do you then let the granules increase in weight throughout the cycle? Do you simulate it like that? Yeah, and then of course you have the coupling of the water and the solids phase. Do the solids impact the water flow, and does the water flow impact the solids? Of course, these two impact each other. It should be, because there's a huge amount of solids You cannot neglect them. We have not accounted for the kinetics here because the specific questions of this project could be solved without. And I'm talking about the specific questions. And it was, for example, mixing of chemicals. What is the optimal? Can we reduce the height of the reactor? We could solve them without the coupling. You can go, of course, further and couple the kinetics to it. Yeah, but it will make it a bit heavier. And if we don't have to do that, we don't do it. Yeah, I hope it answers the question. If not, the person having asked that question can really ask a second one if you want.
If it's not clear, please ask again.
Yeah.
Maybe another question that is quite, it's a curiosity more than a specific question for everyone. What software do we work with? And is there any other software other than Console or Fluent useful for the water industry? And how much have to be customized, these softwares?
Yeah, good question. Well, most of the softwares are generic. So it means they are used across disciplines. For example, ANSYS Fluent is used in aerospace combustion. It's used in in a lot of other industries, process industry, water industry. And then you have others, Flow 3D, Star CCM, I think of Siemens, right? And then we have Console, and then we have OpenFOAM, which is the open source package. I think most of them are quite generic. So I think most of them have very good applicability in the water industry, but we mainly work in ANSYS Fluent as a company. Yeah, because we have a good experience with that. Also integrating the kinetics goes very fast. Of course, yeah, you have to, given the fact that it's a generic software, you have to tailor it a bit to your case. And there, I think, regardless of the software you use, you need some experience. And I think experience in two domains. Preferably, if you're doing CFD, you should have some idea about the technology. So at least know a bit about the treatment technology, or make sure you are next to a person very well understanding this. Second, you need not only know a bit about CFD, you need to have some, I call them flying hours. You need some historical cases and experience to be able to have, I think, very effective CFD work to be done. Yeah. Okay. So I think Flow 3D is a software that is maybe the only one focusing on the water industry, but I mean it's mainly like hydraulics. It's very, very good at hydraulic systems. Less, I think, I am not sure at the process side. Okay, good. Let's go to aeration systems and bioreactors. Why do I show this? Because typically a lot of people have interest in this because it's of very often applied technology. And of course, there is a lot of energy consumption related to it. And we are talking about effluent quality and a lot of other things. Just to show you that we also, as a company, have a very strong history of model validation. So I will come to validation again, because there's a question of many practitioners. But I'm just showing it that we have done really a lot of validation in the past. That's why we do it less and less. And in 80% of the cases, we don't do it. But you can, for example, see that one of our customers gave us a great opportunity in 2017 to have a unique validation. So we looked at, we used the construction crane actually to lower dissolved oxygen sensors in a full-scale wastewater treatment plant. 3 sensors attached, and we moved the crane, and then we had actually in one cross-section a grid of 9 points of oxygen. It was globally unique campaign. We have not seen this anywhere, or not even in published literature. It was quite unique, but we also felt the industry needed it because there is so much skepticism going on. Can you really prove a CFD model is valid? And we just need to show these things sometimes. On the other hand, I don't show them often. Why? Because I directly want to avoid people think if I have to do CFD, I have to hire a construction crane, we have to do these expensive measurements. It's not at all the case. I'm just showing here that CFD is likely to be very accurate if done properly. So what I compare here is the measurement cross-section, so these 9 points of dissolved oxygen in this case, to the simulated cross-sections. Yeah, this is the simulated cross-section. You can of course see in this specific aerated zone that the bubbles actually go to the inner wall. So it's really true, the water flow pushes the whole bubble plume, let's say, to one side, and then let's say 1 or 3 meters above under the surface, they spread again. So if you look at the top, you would say bubbles are very nicely distributed. But in fact, let's say 4, 5, 6 meters under the surface, you have a huge zone where you have lower oxygen and much less bubbles. So the question here we wanted to answer is, can we also measure this? That people really also see that in reality is going on and not only the model is telling this. And we could really see the nice match of the patterns, local DO, where it really is expected to be. We measured gradients in one vertical cross-section right after the aeration zone of more than 200%, actually 197% gradients after an aerated zone. It's what not many people would believe actually, but it's really going on there. Of course, it has an impact on process performance. And of course, if you know this on beforehand, you can actually design systems better, no doubt. Are many systems working well? Luckily, yes. Yeah, but I'm just showing what can be done, and in some cases, it is really a problem. So this was the unique validation case. It's extensively described on our website. We have a whole article on this. Of course, validation, you can also do some velocity measurements. So this is the same plant, but it's not dissolved oxygen, it's actually velocity. So this is again the depth. 0 is the surface, the water surface. -7 is actually the reactor bottom. So it's a 7 meters deep system. And the dots are measurements of velocity, local velocity as function of reactor depth at 3 different points in one cross-section. The solid line is actually the prediction of CFD. And you can see that CFD comes very close to the measurements, given the fact that this is a full-scale facility, which is never in steady state. You always have dynamics at full scale. Well, we have worked a lot on this model throughout the last, let's say, 6, 7 years. It's a very well-established wastewater model that is very accurate. If you would model it as clean water, which some people do, you typically have much less accuracy. If you have much higher accuracy and confidence, you will take much more important decisions based on CFD. And this is where the whole value lies. In this specific case, we could actually directly switch off 6 mixers. It was a rather big plant, so 750,000 population equivalent. That's already towards the bigger plants. If you, of course, can switch off 6 mixers in such a plant, it's a lot of money. It's a lot of energy saving. We could also potentially reduce nitrate in the effluent. Why? Because this local DO, local dissolved oxygen concentration goes down. It sticks near the inner wall, and a bit downstream you have the intake to the anoxic zone. Of course, if you take in much more oxygen in your anoxic zone, you have less denitrification and nitrates go up. So these were all factors we have looked at. It was relevant because they were retrofitting the plant, so the aerators were going to be replaced anyway. And the question the plants gave us, can we now design it very properly, or at least save some energy and also avoid this nitrate issue? So we did a lot of what-if scenario testing without testing on site. We have actually virtually put aerators at different spots. We have switched off mixers. And for example, switching off this pair of mixers or the other one or the third one, they all had a huge impact and a different impact. Yeah. So CFD will give you all these insights, of course. Well, let's come to this question: when to validate? How valid are your CFD models? Because your story looks so nice. How reliable are these things? Do you even validate? A very important question if you're a practitioner. I can say that in 80% of the cases we do not validate. And then the question remains, okay, which are the remaining 20% of the cases then? Well, when to validate? Either the customer really insists and asks for it. Often it's people that use CFD for the first time to take a decision, and they just want to see the data fit on their specific plant. If the customer really asks for it, we will do it, because then the confidence goes up. And if the confidence goes up, the value of the project goes up. Scale-up projects where a lot of stakes are on the game, of course. A new model, we develop a lot of new models. If we developed a new model, we apply it for the first time at full scale. Of course, we will also validate it if we do it for the first time. So these 80% of the cases have a lot of them that we have done like the 10th, 11th, 15th time at full scale. We don't need to validate it anymore because we have proven over and over again that it works. Or in the fourth scenario, the measurement data is readily available. Sometimes there's really a lot of good data readily available, and then we might also validate. Yeah, very important, because if you look at practical application of CFD, it is really practical if you don't have to collect new data, additional data. These are some other types of bioreactors, a carousel type, or like a more plug flow type with baffles. And what I'm showing here is the direct coupling of activated sludge kinetics with CFD. And we look at 3D dissolved oxygen, 3D nitrates, 3D ammonia. We use this model at a routine basis to save energy in plants. For example, people want to keep the same effluent quality, but they want to save energy without risking to lose effluent quality. It's in these cases you will use such a model. Scale up design of new systems. We also use the coupling with the kinetics. So we have a lot of these projects going on. It's quite unique. We are actually the only company worldwide offering this service of the coupling of these biokinetics with CFD on a routine basis. So a lot is possible. Another example, yeah, this is coupling with kinetics in the US. In the US, people now do a lot of sludge fermentation to produce VFAs, volatile fatty acids, but it's actually valid for also fermenters. People also start fermenting now to look at bioplastics formation potential, other things. And again, if you couple this with kinetics, you can see that the local concentrations in one reactor have a huge spread. Yeah, so local VFAs can vary a lot. And then if you do a simple modification of the inlet, so you don't put it at the right side, but you put it at the middle, it gives a huge impact on the effluent quality. It's a nice illustration to just show how sensitive design is to these things. I will come back to Giacomo. Are there additional questions, Giacomo?
Yeah. Actually, there was a question that we skipped before from Osama Amdani. I'm sorry for the pronunciation. Tried my best. The question is, can CFD show channeling in sand filters design and how to avoid during normal operation?
The channeling.
Yeah.
The channeling, I'm not sure, probably it will be in the, well, yeah, that's a good question. I think it will be in the filtration phase. So I will be answering it from the filtration phase perspective. If I'm incorrect, please let me know in the Q&A. But what we now currently look at is just at the particle deposition on the top of the sand mat. So what we are currently not doing is that we start, for example, changing the local permeability due to local falling with particles. It's all possible, but again, in that specific case, we could answer those specific questions with the simple approach. So we don't model the channeling yet. What we of course model is, yeah, how uneven is the distribution of your solids on your particle bed, on your sand bed. Of course, if you start with an uneven distribution, it will lead to channeling. It will lead to a more uneven load of your sand bed in the longer term. So the question is, why wouldn't you start with a homogeneous load of particles in the first place? So already designed for that. So this is where we are right now. If you want to look at that specific question, you need a much more sophisticated model. Okay.
Yeah. So another question was more practical on the validation side. Which equipment we use to measure the velocity profile in depth?
Well, there's a lot of equipment available. I'm talking about PIV. PIV, what is it again? Do you know the abbreviation, Giacomo? PIV?
Not by heart, no.
It's like and then velocimetry. The V is velocimetry, but what we typically use is ADCP. So acoustic Doppler current profiling. Yeah. Yeah. Sometimes. So there are some other devices also possible, but this is currently the bottleneck of these things is they cannot be used in a zone where you aerate. So you can only use them in the non-aerated parts. But often, for us, that's sufficient. Yeah. People use different devices, but we usually use ADCP measurements. Yeah.
So Alessandro gave us the answer: particle image velocimetry.
Okay, thanks a lot. Particle image velocimetry. Yeah. I think it's a bit more sensitive, and it has some different. It's also smaller sensor. It's a different niche application, let's say. Okay, well, I wanted to show also this case because I think it's very interesting to look at. Why? Because it's a huge scale. We already have looked inside membranes. I haven't shown the hollow fiber or let's say, what is the other? Tubular membranes. I mean, we are talking about tiny systems. Well, here we are talking about a huge system. So it's a pond of like 3.3 to 5 million cubic meters. It's a drinking water storage basin. And what you can see is that the flow comes in and that you have actually a short circuit. So the flow really goes to one direction directly after entering the basin. And you are only actually using, this is, by the way, an ADCP measurement. Yeah. This is a boat with an ADCP below it. But I wanted to show this case because people, then you actually also know, okay, CFD can be used also at this huge scale. And in fact, it's not that the simulation will take longer. It's an identical approach. Your mesh size, it's the same maybe. It's just a huge system you can model. So what you can see is that also the simulation predicts this short circuiting to the right. So the flow comes in and it goes directly to the right. And you all see that you only use, let's say, 40% of your basin volume effectively, while everybody would hope that this basin is better mixed and you have less short circuit. So inlet goes to outlet rather directly, and it's a pity for the volume of the basin. What is impacting this a lot, of course, is your basin geometry, but also where you put the aeration. So in such basins, they also typically put aerators. It looks very tiny on this picture. It's this little white ball you see, but actually the aeration is quite significant because the scale is big. And it causes a lot of mixing, but it also causes where you have the short circuit. Can you optimize this? For sure. Can you optimize the aeration flow rate? For sure. And then you can also test it with CFD, of course. By the way, in this case, we have validated this. Why? Because that specific case here was the first time where we applied this model. So we validated. Of course, we have a lot of cases now in the meantime, similar ones where we didn't validate. But you can see, again, same plots. Velocity as function of depth. In some cases, it's 5 meters of depth basin, and in others, you have a depth. The maximum depth was around 20-25 meters in the middle. Well, it's a two-phase model, so it accounts for the water flow, the aeration. We accounted for the influence of wind. On such a huge surface, you have a huge wind impact. Certainly, this was northern Netherlands, close to the sea, while a lot of wind, of course. So this had to be taken into account for the mixing. Good. Just showing this example, we did a lot of stuff here. I can only, on this case, talk for 1 hour. But again, this was not the purpose of this webinar. This is what I'm showing lastly. Why? Because I started with some things which I assumed people would be less familiar with. These things people are more familiar with. It's like flow splitting, flow distribution, typical CFD cases. But I'm just showing them because they are of course very valuable. In this case, this was a new technology. It relied on a flow distribution over the surface, over the bottom actually. It's an A-stage process, so you have a sludge blanket. I will not go into detail. Again, it's on the website. But the thing here is you distribute your influent with a main pipe with lateral pipes. So you want your influent to go into your reactor very homogeneously. Why? Because otherwise your influent is not well distributed. It lowers the kinetics. Otherwise, secondly, you could have a flush out or wash out of sludge. You also don't want this. What you could see in the case they designed initially, that you had a huge dead zone. So a zone that hardly got any influent. And of course, the opposite side, you got much more influent than needed. The problem here was, in this case, the system was already built. It was already in operation. Of course, you can still do CFD to optimize it, but the ideal case is that you use CFD upfront and then build the installation. I mean, if you have to empty a full-scale bioreactor, it costs you a lot of time and money. Only count the operator hours for cleaning, for emptying, and things like that, recommissioning. Well, anyway, we changed some small things in the pipes. Really simple. It's not rocket science, but it really caused the system to be performing really well. You can also see this in what we call the Riemann-Nobels curves. So this is again plots very similar to the shear distribution plots, but here we don't plot shear, we plot the tracer concentration. And in the optimized case, it's almost vertical. So it's a very homogeneous concentration, while in the non-optimized case, you have huge dead zone. Well, coagulant dosing, chemical dosing, a lot of questions. Flow splitting. You can see that if you dose a coagulant, it doesn't mix too rapidly with the water. So if you dose coagulant here, this is the local coagulant concentration. This is the scale. It can go downstream like a very inert stream. We have seen cases where this was really overlooked. And of course, it causes problems because part of your wastewater or your water is not in contact with your coagulant. Secondly, we tested different dosing spots, 1, 2, 3, 5 points in this primary zone here. Well, none of them was the best one. It really wouldn't work. So they actually chose a different technology. Coagulation was very difficult given this design. And they actually went to the A-stage technology, which I showed earlier. But anyway, what we also did was flow splitting efficiency. So you have a wall with 12 holes separating these two compartments. This is actually a grid tank, and this is a primary sedimentation tank. It's a case in New Zealand. Yeah. So we actually did this project fully remotely. It's a 12 hours time difference with Belgium. But anyway, it was a wastewater treatment plant of Auckland. What you saw is the original design, well, it gave a very bad flow splitting in the walls. You had much more flow in the middle holes, of course. We put a baffle here in the CFD model, and then the deviation of the flows was less than 5%. I'm showing this because this is really where most of the water practitioners are familiar with, the typical CFD cases. But they are so practical, and you can reach a lot of results with not too fancy CFD. So I think we should also show this. One of my favorite examples is this one, where we were introducing pure oxygen in an industrial facility. It's a circular tank. The water comes in at the side. And if you look at the bottom, so this is the cross section of the velocity. So the plots here show the velocity. Dark blue is very low velocity. Dark red, yellow is very high local velocity. What you saw is that in the original design, you had a huge dead zone, a lot of risk on local settling of activated sludge. You don't want this. You don't want this in such a system, because these injectors of pure oxygen had to both introduce the oxygen, but also mix. And if mixing is not optimal, there is something wrong. So what we did in this case, why is this my favorite case? Because the only thing we changed, it's really the only thing we changed, is we changed the position of these two devices half a meter, so we move them half a meter from the center line. It's almost invisible on this plot. And we also rotated them with an angle of 15 degrees. So that's all we did. Using the same mixing input, the same energy input, the whole reactor was completely mixed. It was really like a very high velocity, no dead zones, influence was superior, well, had really good mixing with the whole bulk. And this is what you also can see on this Riemann-Opens curve again. Yeah, the whole velocity shifts to the right. So suddenly, without any additional energy input, your whole reactor has a much higher mixing velocity. It's one of my favorite cases because it shows you that very simple and subtle, again, it's often not rocket science, but little decisions can make a huge difference in system performance. They could, due to this, they could save an external recirculation loop. So if they would have designed the system like the first design, they should have included an extra pump and an extra recirculation loop for extra mixing. Okay, one of my favorite cases because it's so simple. Okay, and then you have mixing and storage, drinking water storage, of course, like clean water basements. You don't want water aging, you want plug flow. Mixing chambers where you mix influent with return activated sludge or other mixing applications. Blending. Secondary settlers, very well established in CFD. And flow splitting. Again, very simple, but it's so high impact because if one of your treatment lanes gets 20% less flow, well, it will give you a lot of headaches. And then you have dynamic influent flow. So how do you control the valves? Very straightforward hydraulic CFD modeling, but high value, I would say, certainly in the design phase. Good. Well, just one slide on an additional activity we have ongoing. So it's not all CFD, but it's only for the people right now watching that work on ozonation or advanced oxidation. Well, we have built a dedicated model for that. Why? Because bromate formation, for example, is a big issue. And also people do want to know how much micropollutants they are removing, preferably in real time. And this is where we have built a dedicated model for in this simulation platform, Sumo. So it's not CFD, but I was just showing it for maybe the 1 or 2 or 3 people here watching that have a familiarity with this technology. Okay, so more questions is either me or Giacomo. So Giacomo is also actively working on this. Okay, good. Conclusions. Well, Giacomo, I will first go to you again to see if there are remaining questions.
So maybe this time I will bring a couple of questions.
Daria,
yeah, the first question from Francesco Spanani. He asks he asked if the CFD model could be applied to reactors with aerobic granular biomass.
Mm-hmm. Yeah, good question. Yes, it's very similar than the palette softener. Well, it's not similar, of course, but it's a similar principle than the palette softener reactor I have shown. So yes, granular aerobic granular sludge or anaerobic granular sludge can be modeled with the same methodology. And we have a couple of examples running on that. Unfortunately, I am not allowed to show any of the information on it because it's confidential. But yes, it can be modeled, and it's a very relevant question because the upflow design, again, we have literally seen people struggling with inlet construction for months to years, while you could really have done this with CFD. It's really a very good example there. So you can include the granular sludge, yeah, with a specific density. For example, in anaerobic technologies, we are even looking at different densities, because if you have anaerobic treatment on pulp and paper wastewater, or you have it on food wastewater, the density of your granules is different because of your calcium and things like that. So all of these things can be assessed. Yeah.
Okay, thank you. And then Jan Post is asking about the validation. Are there also cases to use CFD as a validation tool for processes, for example, to save on sampling or real-time monitoring?
To save on real-time monitoring. I don't get the question completely. So if CFD can be used to for validation of technologies, was that the question, Daria?
Yes, yes, yes. To use it, to use CFD as a validation tool for processes.
Well, maybe Jan, you can add a bit more explanation on that, but I will already tentatively, like preliminarily answer it. Well, of course, CFD gives you a lot of insights that you can actually simply not acquire with physical measurements at this resolution. We have many cases where we are one case is the shear. Shear. How do you measure shear in a real installation? It's so difficult. You can also not easily measure local concentrations in a whole system. So yeah, I think if I look at the projects we have done, we have let's say, if I interpret it correctly, again, you can add your comments. We have validated a lot of new technologies with CFD. Yeah, like conceptually, even before construction. Yeah. Other questions, Daria?
Yes, there is one question about the calibration of the model. How to calibrate the model, with which parameters?
Yeah, I think that's a very relevant question. So, well, the thing is, if you look at the computational fluid dynamics model, really the core of it is physical equations, the Navier-Stokes equations, which are very well established. They describe you the motion of the liquids. Well, preferably, we do not calibrate CFD models, because if you don't calibrate CFD models, they keep their mechanistic nature. Once you start tweaking them, you have to do it very carefully. And I think that's more an exercise for academics that really have a lot of data and in-depth investigations. On the other hand, we have cases where you have to, how we like to call it is we add to the complexity of the CFD model. For example, we have shown in activated sludge plants, you can, for example, model mixers using 10 different methodologies. No? It's a very simple one to the most complex one. Of course, we start with the simple one. But if you do validation, you see that it's, in some cases, not enough. Okay, then you go back to the model and we can maybe we choose a more rigor in how we model the impellers. And this gives a lot of gains in some cases. So based on historical validation, we could establish a lot of these frameworks, let's say, for decision making. And on the other hand, you sometimes have to calibrate it. And I'm specifically talking about if you integrate kinetics in CFD, then you might have to calibrate the kinetic model. Yeah.
So maybe as a continuation from the question of Jan, he sent us a message. Wim was right about my question. Indeed, sometimes it's hard to measure low concentration in membrane systems or AOPs. Modeling would validate the process instead. And there is a bit off-topic question from him. Can you also contribute with CFD modeling for very short time effects like hydraulic shocks, water hammers, which can cause big problems in practice?
Yeah. Indeed, yeah, you can. Indeed. So we are indeed the water hammer. I like the name, by the way. I like the terminology. I discovered it like 2 years ago or so for the first time. But anyway, these are transient simulations. So it means you will really dynamically model the flow and then the sudden stop and the whole dynamic pressure field. So these are things we do. We have done a lot of dynamic CFD modeling. Many of the examples I've shown are steady states. So you have not seen too many moving things, but yes, you can model such impacts as well. You can. Yeah.
And maybe one more question from the anonymous attendee. Can CFD simulate long-time processes? And what was the general modeling timescale? And what was the longest time the AM team simulated?
Okay, I don't know if we are talking about process timescale or simulation timescale. Is it process? I think it's process, right? Maria?
Yeah, it's not really written here, but I assume it would be about the process time.
Yeah. Well, I think up till now, Daria, you can testify there. You have simulated this water basin for 24 hours. I think that was one of the most heavy simulations we have done so far. I mean, real time, the time in reality of a dynamic process. We have, I think, we went to 24 hours, but typically we try to limit that. The MBR example, one cycle was 15 minutes. So let's say it varies between minutes, well, seconds to minutes, 2 hours. That's the range. We have not dynamically used CFD to model a process for days or weeks yet. Yeah.
And there is one more question about the water hammer in transient analysis. Is it possible to add with or without the air valve and study the system using CFD?
Well, that's indeed what you also can do. Yeah, I think the air valve is like the cushion, breaking the hammer. Correct me if I'm wrong, but these are things you can in fact include. Yes, if you model the headspace. So it's a two-phase simulation, actually, quite a realistic one. But yes, yeah, we have modeled actually many pressurized systems with a head, like with a gaseous headspace, and then you have a water level. It's always two-phase, and there are approaches for that.
Okay, thank you. And one more question from Jacobo. Is it possible to model the biokinetics of activated sludge with CFD?
Was that from Giacomo from our team or somebody?
No, it's from Jacopo Ducci.
Okay. Well, sorry if I didn't explain it too very well, but yes, because I have shown actually some examples on this. I will go back. Sorry for the many slides on the screen. But this is one example on the screen right now where we have coupled biokinetics with CFD. So we do it actually on a routine basis. I think we currently have like 4 to 5 projects only on this going on. The bottom facility here is a huge facility in the US, industrial wastewater treatment. And then we have coupled, modeled the whole anoxic and aerobic zone with CFD plus biokinetics. Yeah, for again specific reasons, energy savings, process optimization. Yeah, so it's perfectly possible, and it's not only possible. I would say it's very well established. Well, we have at least really applied it at many facilities. Yeah.
Thank you. And I see one more question from Alessandro, a general question about cloud computing. Is it going to be widely used in the future? Are there pro and contra according to your experience?
Well, I try to read a lot of books on this stuff because I'm intrigued by such developments. And I think the general trend is computation power only gets higher and higher and only gets cheaper and cheaper. So I believe in really, like, look at just your cell phone. They are now experimenting with 5G. And then whatever they will invent then. 5G in the beginning will cost some money. And after some years, it will almost be for free. And then 4G will maybe turn free. Things get commoditized. So even cloud computing, I strongly believe in that it will even get very cheap in the future. So, and then if you go then for the more expensive options, you will have a huge power horse, of course. So that's my prediction, that we shouldn't be too scared about limitations there in the future because it will keep evolving. Yes, it's not Moore's law anymore. Moore's law is like doubling every half a year of the computation capacity. It's a bit slowing down, but yeah, slowing down, and it's still significant. I strongly believe in such things. Also, distributed computing, so you don't always need a physical server at one spot. Why not distribute it across many PCs? Of course, Bitcoin mining, I'm not an expert there, but it's a similar system. So it's not only computing power, it's also smart networks, using AI to control computing. I mean, I think the sky is the limit in the future. I mean, when in 10, 20, 30 years from now, yeah, it will be another ball game. Huh? Yeah, that's my prediction. I'm just predicting the future.
Okay, thank you for your answer.
Other
That
questions
was
from the audience?
that was the last question. So thank you for the answers, Wim.
Thanks for asking the questions, Daria. In that. Okay, I think I went well over time. Sorry for that, but I'm really glad to see that still 26 people are here. So you are really hardcore attendees. I congratulate you for that, because it's really not at all easy. Huh? Keep listening for so long on such content. So congratulations for that. Okay, I think we can close here. What is important is that if you close here, a link will appear. It would really be great if you could fill in the questionnaire. It will take not even 1 minute of your time. Second, you will get a follow-up email from my email address. And if you have specific questions left, just reply that email, send me an email, and we can take it further. Yeah. So we will try to leave no questions unanswered. So feel free to contact us. Also, feel free to follow us, especially on LinkedIn, because on LinkedIn we always put our latest material and a lot of blog posts and stuff. Okay, we will close here. Thanks so much for joining and for staying so long. And I really hope that we can see each other again, virtually or in reality, if it's possible. Bye-bye. Thanks, everyone.